Okay. Right. Right. Oh, too many things. Okay. So, any questions? So get started today? No? Okay. In that case, so, okay. So we're we started to look at this binomial distribution, and it's a family of functions of probability distributions, and it's what's known as a discrete probability distribution. And basically what it is it's a tool, and it's designed to help you solve a very specific kind of a problem. Okay, and so really, I mean, what we're looking at, what we're examining, is, you know, a bunch of these problems, and they'll all have certain characteristics. Okay, and so what are those characteristics? And as soon as you find a problem that fulfills those characteristics, you know that you have a binomial problem, and then you use all of the binomial stuff to solve it. Okay, so what's the checklist? So this is what you're looking for. Okay, you're looking for, are there n identical trials? So think of tossing a coin. So is the problem that you're reading sort of kind of like tossing a coin, except that, you know, the problem may not be a fair coin. Okay, but you sort of start with tossing a coin. So are there, you know, 2 tosses, 3 tosses, 20 tosses, you know, things that are repeated. And then for each trial or each run that is repeated, for each run that's repeated, does it result in something that you can construe, or does it seem like there's a success or failure, sort of like a heads or a tails, you know, a yes or no, on time, not on time, you know, in default or not in default, you know, is it, sometimes it's not obvious, and that you could do this or that, you know, the 0 or 1 binary outcome. But if you can cast it or frame it that way, then it could be binomial, right? Then, you know, does the probability of success remain constant? So sometimes it changes. So in our problems, yes, they will remain constant. And then, is each of the trials independent, right? And so every additional one that you do does not depend on the previous one. Okay, and so generally, you know, in our class, a 200 level class, the problems that we'll have will basically all satisfy, the ones that are geared for the binomial distribution, they'll all satisfy it. Okay, but in general, this is what you want to look for. And if you spot this, then it's like, you know, we're building this tool chest of frameworks in this class. And the first tool was, you know, cost, volume, profit, and this break-even point kind of a thing. Mixed cost, you know, a variable cost, fixed cost, mixed cost, right? Then we started to do time value of money frameworks with interest rates and compounding, and that's sort of another tool in your tool chest. And then this other main tool is this binomial distribution, or, you know, probability and events, and now the binomial distribution. So that's a tool. So once you read a problem and you believe, or you identify it as a binomial distribution, then you go, aha, you metaphorically reach into your applied math and business framework toolkit, and you pull out the binomial distribution, and they're all the same. Okay, you'll find out that once you do a few of these binomial distribution problems, they're like all the same. And so once you spot it, then it's kind of an old friend and you're back on home ground. Okay, so this problem, right, says at a particular store, 60% of shoppers will use their loyalty points to receive some sort of a discount at checkout. What is the probability that each of the next 5 shoppers will receive some sort of a discount from using their loyalty points? Of the next 5 shoppers, how many would you expect to use their loyalty points, and how likely is that expected value? Then of the next 5 shoppers, how likely is the number of shoppers who use their loyalty point to be within 1 standard deviation of the mean? So that's kind of a really statisticsy question. But the others are, more natural, perhaps, right? So, you might say, read this and see the 60%, right? 60% will use their loyalty points, right? And then it's kind of asking about, 5 shoppers, right? Of the next 5 shoppers, right? And so you might say, there's no interest rate here, right? There's nothing about variable costs and fixed costs, no events, right? But it's asking about these probabilities. And so you might think, maybe this is a binomial distribution problem. Okay, so are there n identical trials, right? Yes, so in that case, n in this problem is, right, binomial distribution, right, I should mention, right, we're basically looking for this B and P parameters, right? And if we find these numbers, these parameters, then we for sure know that we have a binomial problem. And in fact, we're going to use a particular member of the binomial distribution family to help answer the questions, right? So here, are they identical, like the next 5 shoppers? Okay, you assume that all 5 of the shoppers are independent, right? So we'll say, yes, they are identical. So how many repeats are there? How many trials are there? There are 5, right? 5. Okay. And then does each trial result in either some kind of a success or failure, right? And so it's use loyalty points or maybe not use loyalty points, right? So that's binary, so there's a probability of success or failure, right? And that's 60%, right? So we'll say 0.6, right? So the B and P that we'll be using is 5 and 0.6. Okay? And so, and then you should continue. Does the probability of success remain constant? It says, 60% will use their loyalty points. This is probably an empirical probability, right? And so, or maybe they're just beginning their analysis of this, and so they might say, well, we'll just assume that it's 50, that it's constant. Okay, so we'll say yes. And then is each of the trials independent? And we'll just say yes. Okay, so then in that case, use B5 0.6. Okay, so as soon as you see B 5 0.6, what should go off in your mind? Okay, so hopefully, right? Let's see. I'm gonna do this. Yeah. So hopefully something maybe not quite like this, but perhaps something like this will go off in your mind. It's kind of sorry. It's kind of like buried over here, but there's probability mass function. Okay, and all of these probabilities add up to 1. Right? And then you can see how this one is a little bit skewed, right? It's a little bit pushed. It's not, even, Why would you expect it to be skewed or pushed over? Because it's not 50-50, right? If the probability of success, P, and its complement, Q, 1 minus the probability of success, are 50%, then is 50-50, and so then you would expect this thing to be even, the probability mass function to be symmetric, right? Here, the probability of success is 0.6, so it's a little bit skewed. It's a little bit pushed over to this side, right? And so, so you know, kind of the midway point, right? 5. The midway point would be 2.5. So the ones on the left of the midway point are kind of pushed down a little bit. So you can see that they're kind of, and then because everything has to add up to 1, right? If half of them, roughly, right, are kind of pushed down, right, then the other half of them are kind of pushed up, right? And so, in fact, the end point one here at the very end, the tail, is higher than this other one, right? Because it's more likely, they're a little bit more likely to use their points, okay, than not use their points. Okay, so something like this, you know, and then as soon as you write down, you know that, right? Because why? Because it's binomial. It's a family of distributions. You know, we looked in more detail at the 2 and the 3 case. Now we're starting to look at the 5 case. But you know, they're all about the same. And then based on this probability of success, or you know, whatever, it could be skewed the other way. If this is 0.2, you know, less than 0.5, it's kind of skewed to the 0 side, versus if it's more than 0.5, then it's skewed to the high side. Okay. The other thing that we've looked at is we've looked at the sample space. Okay, although we've never looked at the sample space quite like this before. Okay, and so here everything is kind of different, but it's really the same in a certain sense, right? So if there are 5 tosses of the coin, or in this case 5 customers, or you know, there's 5 events, or there's 5 things, you know, that are repeated, trials are repeated, 5 you know, component experiments that are subparts that are repeated, and if each of them could be success or failure, true or false, 1 or 0, how many different possibilities are there, right? Well, you know, you just sort of think there's the first one, the second one, the third one, the fourth one, the fifth one. So the first one, there's 2 ways. Second one, there's 2 ways. Third one, there's 2 ways. Fourth one, there's 2 ways. Fifth one, there's 2 ways, right? So really, that comes out to be 2 to the 5th. So there's really 32 possibilities, right? 2 to the 5th is 32. But they actually fall into these families. Okay, and so last time we talked about the Pascal's triangle a little bit, and you know, hopefully this you see that this is really one row, if you will, of the Pascal's triangle. You know, sort of 1 on the low side, 1 on the high side, and then actually, if you remember how we built the Pascal's triangle, so if we were doing the 6, right, we would put a 1 over there, right, and then we would put a 1 over there, and then to get this one, we would combine those, and so this would be 6, right, and so we would combine those, and this would be 6, right, so we don't want to sort of mess things up too much, but this one, you know, it's the low one is always 1, the high one, the coefficient, is always 1, okay, and then the next one in, there's always like the number of the row, right? And you know, so what's going on, right? So this Pascal's triangle, or these combination coefficients, as we'll see, you know, let me just see if I can conjure up my calculator here quickly. That one. Oh, come on. Anyway, the C thing is on the calculator, right? It's I think it's right above the sorry, here we go, right above the plus sign. Okay, so what we're talking about is we're talking this NCR, which is a second plus over there. Okay, so that's what we're talking about. And what this group is this is the group of where there's, say, so the way that you read it is that this is the n, NCR, is this is the total number of trials. So you see that in all of these coefficients here, this is the 5, C55. Here, this is C54, C53, C52, C51, C50. So the n in all of them is this head row. Okay, so that's the number of trials. Okay, and so in these, the n is the number of trials. Okay, so what's the R, the second one, is the number of successes. Okay, and so this C55 is, if there are 5 trials, tell me how many there are if there are 5 successes. And there's only one. So the answer is 1, and that means that there's only one group like that. Okay, so if we go to the calculator, right, and we do 5, and then we do the second NCR, and then 5, and say equal, we get 1. Okay, and what is that telling us? That's telling us that if there's 5 things and I choose, 5 of them, and they're unordered, actually, because the order doesn't matter. There's only one group like that. Okay. So the second one is 54, C54. So this is now saying, okay, there's 5 total possible elements. Okay, and I'm choosing C. I'm choosing 4 of them, and order doesn't matter. Okay, how many are there, right? So that will be 5, and then this combination, and then now instead of 5, it's 4. And so it tells you there's 5 of them. And so what that's telling you is that if you have 5 elements and you want 4 of them to be successes, how many ways are there? And this is telling you there's 5. And so here we wrote them out, right? So how many, if there's 5, and there's 4 successes, well, the first 4 could be a success, and then the last one could be a failure. The first 3, and then number 4, failure, and then the last one, okay, and then 2 in the beginning, the middle, no, and then 2 at the end, or kind of mirror of this one, but success first, and then false, and then the other 3 to make 4. Or the first one is false, and then, or failure, and then the next 4 in a row are, right? And so this exhausts the 5. That's it. Okay, so this other coefficient, C53, is, okay, now there's 5 elements, and now I want 3 successes. Okay, so that's, again, I want to use the C53, right? So here's the, here's, here's the 5, okay? Here's second NCR, and then we want 3. Okay, and so that's telling you there are 10 ways. There are 10 ways, okay? And so in this case, we sort of wrote them all out here, and there are 10 of them. Okay, and so the other case, here there's 5, but now only 2 are successes. Actually, you can see that they're kind of the mirror of each other, right? Where here, wherever you have success, you just have the failure, right? And so in this case, there's 3, all of these groups have 3 successes and 2 failures. Here, it's just the opposite. There's 2 successes and 3 failures, and so they are kind of mirror, quote unquote, mirror images of each other. But for every one that has 3 successes and 2 failures, there's the one that has 2 successes and 3 failures, right? The other way around. And so that's why they're symmetric. And that's why this one's symmetric, right? Because if there's 4 successes and there's only 2 possibilities, the one is a failure, right? So here, if there's 5 things and then 1 is a success, if there's 5, the other 4 have to be failures, right? So these 2 are kind of mirrors of each other, and then of course those at the end are kind of mirrors of each other. Okay, and so just to be complete, right, we'll do the 5 C2, right, and that, oh, sorry, I must have done something weird. Second, C2, 5C2 is 10, and then the 5 C1 would be 5, so we did that one first, and that was C2. Now let's do 5C1, and then now when we do 5C0, so this is, if there's 5 things, and what is, and there are no successes, or yeah, there's no successes, how many different cases are there? Well, if they're all failure, there's only one way to do that. Okay, so that's kind of how these combination coefficients, that's what they mean, and that's kind of how they arise. And so it's important to remember that this NCR function, that's what it gives you. Okay, so anytime, really, anytime you have a larger set, you know, n, and you want to draw from that a subset, and the order does not matter, then you use this function. Okay, and so here it's important for, here it appears in the binomial distribution, but it also appears in many, many other cases. Okay, and so, by the way, you know, remember that what does this success mean? It means that the first one was a success, you know, and the second one was a success, and the third one, and the fourth one, right? And so we know from independence of probability when we have and, that's the intersection of all of those, and we can multiply those probabilities. So we would multiply 5, as in this second number is 5. Okay? So marching right along, we know that, you know, when we deal with these binomial distribution problems, right? When we deal with these binomial distribution problems, sometimes you want to know if there's 5 total possible, what's the probability of success of 4 of them? Well, you could have this one, you know, success first, success first, and success third, and success third, and failure fifth, or you could have this one, or this one, or this one, or this one. So each of these, since the multiplying for the intersection, the multiplying doesn't matter. So it doesn't matter if we multiply, you know, 0.6, 0.6, 0.6, 0.6 times 0.4, or 0.6, 0.6, 0.6 times 0.4 times 0.6, right? Or 0.6, 0.6, 0.4, right? It doesn't matter if we, the order of multiplication. So we might as well pull it out into this form for the intersection, and then there's 5 of them, right? Or so they're mutually exclusive, and so because there's 5 cases, we can add those cases together. Does that make sense? So we're kind of using independence for each individual one to get that multiplication, and then we're using this union, or because they're mutually exclusive, we just add them all up. Okay, so that's how we bring in concepts from last week. And then same thing here, right? Because what this means is that there are 3 successes. Okay, so that means we know that it was successful 3 of the times, so we have 0.6 cubed, right? Because there's 3 of those. And then if 3 of them were success, the other 2 were failure, so the q is the complement 1 minus p, 1 minus 0.6, that's 0.4 in this case, and so we square it because there's 2 of them. Okay, and so again, we know that from the Pascal's triangle or the coefficient, we know there's 10 of these cases, and so that's how we multiply by 10. Okay, and same thing for here, it's just a mirror of that. So we raise the success to the second power, we square that, and then we cube the failure in this case, right? So it looks symmetric, and obviously if you're back in the case of the fair coin, 50-50, these guys, the P's is 50% and the Q is 50%, and everything's the same. But here, if it's skewed, this is how you handle it. Okay, and so this one is kind of the mirror of that one, right? And this one is kind of the mirror of that one, and this one, in a certain sense, is kind of the mirror of that one. Okay, does that make sense? So as soon as you read this problem, right, and you spot it as a binomial, you might think of this. The first thing you might think of is oh, okay, so it's got this probably mass function. This is the one that looks like a comb, right? Here we actually have the graph, but without drawing the graph, you know that it's a little bit skewed, right? You know that these are pushed down a little bit, and then these are pushed up, because all of them have to sum up to 1. And so if you push these down, what you push down, it has to go somewhere. So in some fashion, it goes, the ones from the left go to the ones on the right. Okay, so somehow it looks like that. Furthermore, you know that it has a structure, or maybe you didn't quite realize that, but you know that there's a certain number of them. There's a fixed number of them based on how many there are, and against 2, so it's either success or failure, so you just raise it to the power. So there's a certain number, that's the sample space, right? Total number. And then maybe you kind of got the feeling that there was some kind of a pattern. But here it is now. Okay? And actually, if you really look at this coefficient, you could multiply it by 1, right? Any time you see any value, you can multiply it by 1, and it's the same, right? Multiplying by 1 is the same. So q raised to the 0 power would be 1. And so you can actually imagine in your mind, or pretend in your mind, that it's actually n minus r. So q is always n minus r. So you see the power of the success is going down, right? So 5, 4, 3, 2, 1, and then 0, right? So you could imagine that there is a p there, but that the p is raised to the 0 power, and that in multiplication sense it goes away, right? Additively, if you add by 0, that's when it goes away. But by multiplying, you can multiply by 1, or in this case, p to the 0 power, right? And that's 1. So you can sort of imagine that there is a p to the 0 power. And so, if you imagine it that way, you can actually have this expression for the whole coefficient. And by the way, we've been thinking about this NCR. There's this other function called factorial, right? Factorial is right up there above the multiplication. So factorial is actually related to this p, which is the permutation function NPR, and then the NCR. So these functions are actually all related. In fact, of the three, factorial is the largest, and then the permutations will be a little bit smaller, but still larger than the combinations, the C, and that will be the smallest of the set of three functions. But we'll say a little bit more about that later. But if you did ever want to compute the C from its raw form, you take the n and you do factorial. That's your numerator. Okay. Then you take the n and then you subtract r and you take factorial. That's your first division. And then you just take r factorial and you just divide it again. It really looks kind of intimidating, but if you just think about it this way, it's just a mechanical formula where this first one goes in the numerator as a factorial. Okay, that's the biggest one. And then you just take n minus r and you do that factorial and then you divide it in. And then you just take r itself and then you just divide it in. And so that's actually what it is. So this is sort of the formula in its full glory. And by the way, this whole thing comes out to 1, right? Because here you have 5 minus 5, and then you have to know that 0 factorial equals 1. Okay, so really, it's like you take 5 in the factorial in the numerator, and then if r is 5, then you put 5 factorial in the denominator, and then whatever, you don't even have to know what the number is because that cancels out, and then you're left with 0 factorial, so it's 1. So that's basically how you get this one also, where here you have the 5 factorial just like that, but now r is 0, so this side is 0, right? Over here, sort of this side is 0. Here, this side is 0. The other one is 5 minus 0, so over there it was 5 minus 5, now it's 5 minus 0. So here's the 5 factorial, so then it cancels out to there. The next one up, 5 factorial, so r is 1 factorial, and so 5 minus 1 is 4 factorial, and so really this coefficient, it's 5 factorial divided by 5 times 4 factorial, right? Because if you see that 5 factorial there, you can change that to 5 sorry. You can change it's 4 factorial. 4 factorial. And so what this is really 5 times 4 factorial over 4 factorial, right? And then so the factorials cancel, and so what's left is 5. Okay, 5. Okay, so I just want you to sort of see these in case you look at a book or you read a book and you see this thing. Just remember that it's just this combination that's related to Pascal's triangle, and really it's telling you the number of events where if you have a total of 5 things, 3 of them are success, say. Right, and then the other 2 are failure. Okay, and so that's actually how you compute it. Okay, so each of these basically comes out to a probability, right? So this is the probability of success, right? And Excel has this same, or has a binomial distribution function, right? The second and third values are the n and p, right? And then the first value of the function is basically r, which is the number of successes. Okay, and so whether you use the function in Excel to give you the probability mass function, or you dare challenge yourself to compute it the long way, what it's really doing is it's say for this one, the probability of success, 3 probabilities of success, it's taking this probability of success cubed, which in this case would be 0.6 cubed, and then the other 2 cases, if 3 are success, then we know there's 2 failure, and its probability is the complement, 1 minus p, 0.4 in this case, and so it's squaring that, and then it's realizing, it's realizing this case, hey, there's 10 of them, so that's where this 10 coefficient comes from. Okay, and so these values are a little bit different because the coefficients are the same and the p's and the q's are the same, right? But the exponent is a little bit different. This one is coming in with 3 at 0.6 and 2 factors at 0.4, so it's a little bit larger. This one is coming in with 2 at 0.6 and 3 at 0.4 factors multiplying, so it's a little bit less than that. Okay, so as soon as you read this problem and sort of write this down, you actually can already know all of that, right? It should sort of kind of percolate in the back of your mind. As soon as you write down this B56, what is that, right? That is a member of the binomial probability distribution. It kind of looks like this. We sometimes, up to now we've been seeing it sort of in this table form, but really it's this one plus 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 this one. The probability equals 1, and so you could see it in a line or you could see it, in this table, or you could see it in its probability mass function or the continuous distribution function. Okay, so all of that should, hopefully by now, kind of come into your mind that, oh, okay, this is just another one of the same thing, and been there, done that, so it's going to be easy, right? Hopefully. So anyway, what is the probability that each of the next 5 shoppers will receive some sort of discount from using their loyalty points? So how do we do this one? How do we do this one? Okay, so you have to remember that, sort of math, unfortunately, or whatever, math is like the opposite of English class, right? English class, you will really use these long, juicy adjectives and, describe things and vary your language around so that, your readers don't get bored, right? Math is really the opposite of that, right? As I said before, you want to abstract everything. You want to, what's not important, you want to throw away because you don't want to be distracted by it. You want to bring it down to its essence. And then once you see its essence, then you can apply all of these other properties to it. Okay? So how do we figure out what's the probability that each of the next shoppers will receive some sort of a discount from using their loyalty points? How can we figure that out? How can we figure this out? So when we work with these probability problems, what are some of the tools that we need to assemble? What are some of the tools we need to put together to get started? What should we use? We kind of have this distribution, probability distribution, lurking over there. So how do we use a probability distribution? Probability distributions, right? We connect them to something. What do we connect them to? Right, maybe we went and we looked at all of these things. What do we call these things? Oh, these are the combination coefficients up here. Yes, on the right track. But what are these? Like this one, or that one, or that one. These are the underlying what? Yeah, or events, right? Elements, right? These are the actual events that happen, the underlying events, right? This is supposed to model 5 shoppers. So the first one, the second one, the third one, the fourth one, the fifth one. Another event could be, right, this event. Another one could be this event. Another one could be this event. Another one could be that event. Another one could be that event. Another one could be that event. Which one do we have? I don't know, right? Because we don't know. But we do know we have one of these, right? We do know that we have one of them, okay? But which one, I don't know. We don't know. And so how do we denote, the fact that we've got one of these from this sample space, but we don't know which one? There's a structure or a tool or a something that stands for the outcome that we don't know. when you have an unknown in math, what is your unknown? The unknown is your if you don't know something in math, that doesn't stop you. You say, well, I don't know what it is, but we might know some certain things about it. So let's call it a any ideas? Variable, right. So some kind of a variable. Right? So we don't know what it is, but we know some things about it, like what it adds up to or this or that, right? And in this case, it's not your ordinary algebraic variable because it's got to take on one of these variables or one of these it's related to one of these events, right, that happen at random. So what kind of a variable is it? It's an RV. RV is a random variable, right? Random. Okay, random variable. Okay, so so we know we're going to use this distribution, so we have to have a random variable first, right? So once we have a random variable, then we connect the random variable to the probability distribution, right? So what would a good random variable be? Maybe we'll just call it R for the sake of random. Or, so if we let R, what should we let our random variable be? Usually for the binomial distribution problems, you let your random variable, what's the usual random variable, for binomial problems? Usual random variable is, let the random variable be the what? The count, right? Count the number of what? Count the number of successes. Is that right? Does that sound familiar? Right? When I count the number of successes, in this case, right, the number of successes is will use loyalty points, right? So here it's will use loyalty points. Okay, so you let R count the number of successes, or R count the number of shoppers who will use their loyalty points. Okay, and then we set R to have the be distributed as this binomial with 5, 0.6. Okay, so now we have this as a setup, right? Background, backdrop. We're ready to roll. Okay, so what do we do? Right, we have to translate this one into the framework. Right, so how do we do that? Right, what is the probability? Right, so we want to do P, right? What's the probability that what? Something about this R, and then it's either going to be some value. So what's the probability that each of the next 5 shoppers will receive some sort of a discount from their loyalty points? So you want the probability that R, what? What about R? Right, thank you. That R equals 5. Good. So each of the next 5 shoppers, so you could think each of the next 5 shoppers will receive, right? So that's sort of S1, S2, S3, S4, success, S5. So meaning success first, success. So all the first 5 are all successes, but you know, those probabilities are all the same, right? So instead of doing S1, S2, S3, S4, S5, we can just say success, 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 right? So that is the case that all of them are success, R equal 5. So if we jump ahead, right, so how can we do this? This is equal to what? Probability of success is what? Probability of success is P, and that's 0.6. And how many of them do we have? 5. Okay, that's it. So if we, the exponent is this y to the x, right? So we want to do 0.6 to the 5th power, so we do 0.6. And then when we push y to the x, now that first number that was there, the 0.6 kind of goes to y. And then the second number that we push in is that's x. Okay, so y to the x means the first one we pushed in, which is now the 0.6. So that becomes that sort of base. And then the one that we see now is our x. And so that's the exponent, right? So that's what we want. And so it's equal to 0.0778. So it's you know, approximately equal to 0.00778. Okay, and so actually, you know, I guess I rounded it a tiny bit. Okay, so you could do this whole function in Excel, right? But all it's doing for this one, right, and sort of this other one would be 0.4 to the 5th power. It's just doing this. Okay, so I mean, for the other ones with the coefficient, you know, and this, it's a little bit more tricky to key in. But at least the very, very first one and the very, very last one, those are easy. But you can actually sort of knock those off, right, as we just did. Okay? So of the next 5 shoppers, how many would you expect to use their loyalty points, and how likely is that expected value? So how many would you expect to use their loyalty points? Oh, how do you know? 3 over 5 is 0.6. That's on the right track, but we want to know how many we would expect. And so as soon as you see that word expect, what do you think of? Expected value, right? So we want the expected value of R. What's the expected value of R? Right, the expected value. So because it's, you know, B N P, it's equal to NP. So in this case, N is 5, and the P is 0.6, right? And so it's 3, right? Because 5 times 6 is 30. And then you have the decimal point. So it's 3. Okay, so you would expect 3 to do them. And how likely is that expected value? How likely is that expected value? So we know that there's 3 probabilities of success. So what does that mean? Probability of success is how much? 0.6, right? So we know that we have 0.6 cubed. And so if we have 0.6 cubed, we have 0.6 cubed, right? But we know that we need 5 of them, right? Or not need 5 of them, but we know that we have 5 total, right? So 3 of them are success, right? And if 3 of them are success and we have 5 of them, then the other 2 are failure, right? And so what's the probability of failure? 0.4, right? 1 minus 0.6. Okay. And so if you think ahead, right, knowing what we know now, right, we're really in this case where there's 3 successes and 2 failures, and it doesn't matter. It doesn't matter what order they're in, because we want to know of the next 5, what's the probability that 3 of them use their loyalty points. So we don't care if it's the first 3 or this 2 and that last one, the first one and the 4th and 5th. We don't care which order the 3, how you get the 3. We just care of the 5, which 3 of the 5, 3 are success and 3 are failure. We don't care of the order within that group, right? So now we have the probability for one of them, but we have to get all of them, right? And so actually we can say that we know that there's 5 and we want the 3. Does that make sense? Make sense? Okay. So actually we can do that, right? We can do 0.6, 0.6, and then y to the x3. So now the 0.6 is my base, and that sort of got shifted over up into y. And this 3 that I see is now the x. So that's this one. Okay. So let me multiply now by 0.4 squared. Okay. So let me store this in 0. Okay. So then I can do this coefficient, which is the 5c3. Of course, we knew it was 10, right? We knew it was 10. Now what I would like to do is I would like to multiply it by that one. So actually, I could do stow times that, or I can also do times, and then if I recall 0, I bring that out, and we get this. 0.346, right? 0.346. So hopefully 346. Okay. So that's actually what we did. So you can if you just need one of those probabilities, it's not so bad to get it from the calculator, right? You just have to understand. I mean, it helps if you sort of see this whole big picture, right? And then you understand, where you are in the probability mass function, right? So some of these questions are like that, right? So of the next 5 shoppers, how many would you expect to use their loyalty points? Expected value. Usually you have to do this process, add them all up, or the weighted average kind of a thing. But the binomial distribution has a special property where it's just NP. So now we expect 3 to use their loyalty points. So how likely, what's the probability of that? How likely is that expected value? So it's 0.346. So if we want to, we have the luxury, right, of having this little probability mass graph. And so this is actually the expected value, 3. And we can see that it's the highest, it's 0.3456. Oh, wow, 3456. I just noticed that. Okay? So, how likely is effective value? Oh, we got that. How likely is effective value? Okay, we got that. Okay, so of the next 5 shoppers, how many within 1 standard deviation of the mean? So now this is sort of a really more of a statistics question. It's more of a statistics question. But that's kind of where we want to go, right? We kind of want to go into statistics. So we have this mean, right? And there's this sigma, there's this standard deviation, right? And so sort of around the mean, sort of 1 sigma down and 1 standard deviation above, that's informally, people kind of think of that sort of as like the sweet spot of a distribution, right? So, within 1 standard deviation of the mean. So, some probability distribution, it's kind of like that, right? And then somewhere there's a mean. And then you kind of want to know something about the variation about it. So this one, say, is mu minus sigma on the low side. And then this would be mu plus sigma on the right side, right? So I should just say this one is the Greek letter mu, and typically it's the mean or average. Okay, and then this one is the Greek letter sigma, and it's the standard deviation. Maybe you've seen this thing. So this is the capital or uppercase sigma. Okay, and then this one is the lowercase. Okay, so big, like the summation sigma, and then that's the lowercase sigma, and then of course the sigma squared. Sigma squared is the variance. Okay, and so how many shoppers are within 1 standard deviation of the mean? So what we want to do is we want to find mu minus sigma and this interval mu plus sigma, right? And so clearly we already found the mean, right? So what we want to do is we want to know something to the left of 3 and something to the right of 3. And so basically we need to find what is sigma. So how do we find the standard deviation really quickly? Sorry? Almost. Something about this NP. What's the simplest thing that's related to NP that's not NP? Right? How about NPQ, right? Where if Q is the complement of P, it's really N times P times 1 minus P. Right? So if you can remember, you sort of do have to remember, a few tricks, right? So it's good to remember the expected value, the mean of a binomial is NP. So then the next one up, variance equals NPQ, right? So in this case, it's 5 times 0.6 times 0.4. So remember that this is 3, right? So times 0.4 is equal to 1.2, right? Okay, so then that's the variance, and the variance, you have to remember, is the standard deviation squared. So this is, so sigma squared is equal to 1.2. So this means that sigma is equal to the square root of sigma squared, which obviously in this case is the square root of 1.2. So sigma is equal to 1.2, and then we take the square root. So it's 1.095. I guess I should say that's approximately equal to. And then we'll just call it, say, 1.1, basically. Okay, so how many within one standard deviation of the mean? So this mu, let's say mu minus sigma, comma, mu plus sigma. Right, so that's basically 1.9, is that right? To 4.1, right? Because we take 3 minus 1.1 and we take 3 plus 1.1. Okay, so basically this means that we got 2, we got 3, and we got 4. Okay, so if we go back to our probability mass function picture, the sigma is 1.1, and so it extends like that. Okay, and so inside this we have 2 and 3 and 4. And so if we want, it's not asking what's the probability of those, we would have to add the probability of 2 and the probability of 3 and the probability of 4. And so that's where we would expect most of the occurrences to come in. So the expected value is 3, but that's only like 0.3 of the time, so that's not that often. If we include 2, 3, and 4, you can see that already this one and this one, the 3 and the 4 and the 2 already, those are like 0.25 and 0.25, so that's like half. So plus this, it's like 85%. So 85% likely to be 2, 3, or 4. So you would expect 3, but 80% of the time you got 2, 3, or 4. So that's what you would. Instead of the expected value being just 1 point, which only happens, that we know, is 1/3 of the time. That is the expected value, but the likelihood of that is really only 1/3 of the time. So now if you sort of extend that to one standard deviation below and one standard deviation above, that is going to capture like 80%. So 80% of the time you're going to get 2, 3, or 4. Does that make sense? So depending on what your question is, you may have a slightly different calculation. Yeah? Does that make sense? Okay. This is just some detail on how to calculate each of the values in the calculator. So the one that we did was actually this one, right? Where here it was storing it in 3, and then it was doing the stow times 3, and then recall the 3. Okay, and so if you really wanted to go, so we kind of just did this one. If you wanted to do more of them, this is another example. So here, though, I did times and then recall 3 equal to get that. But this is a slightly different way. Okay, so that hopefully gives you a better understanding of how to apply this binomial distribution. next, oh yeah, so when you see, the loyalty points, so, when you want to try to understand a distribution or a histogram, what are the usual first and second properties asked? So you want to know the center and the spread. So what gives you the center of the distribution? What gives you the center? Right, the center is the expected value, or mean. Also, there's this other value called the median. Okay, so understanding the center is very important, right? And so there's a few slightly different and a few slightly related ways to do that. Or anytime you have sort of one concept that goes by a couple names, it is really important because, in one field it's known by this, in another field it's known by that, and so that is a tip-off. Once you know sort of where the middle is, then you might want to understand, well, how spread out is it, right? And so there's several measures for spread, right? One that we are talking about is this idea of variance and standard deviation. Okay. Other measures would be, say, the minimum and the maximum. Sometimes that's known as a range. Okay, and so all of those can give you some idea about the spread. Also, this sort of mu minus sigma, comma, mu plus sigma that we just did, what's the probability within one standard deviation of the mean? Within one standard deviation of the mean, that sometimes that's called the IQR, the interquartile range. And so that also is another measure of spread. You might hear, in Business 310, you'll also not only look at the mean, the variance, you'll also look at the skewness and the kurtosis. So skewness is whether it's shifted to the left or to the right. So here it's shifted a little bit negatively, shall we say, because the tail is a little bit longer to this side. And then, so skewness is sort of left or right, and then it could be flattened or more peaked, right? And so the kurtosis is another measure of that. And so you will want to talk about the shape of a distribution. But right now, we'll just deal with center and spread, and then just know that there are a couple others, skewness, left or right, and then whether it's peaked. So if it's peaked, then the tails will be pushed down, and then if it's not peaked, and then the middle is pushed down, and the tails are higher. There's more stuff in the tails. So that's basically that. Oh yeah, so that's how we think of the discrete distributions. When we go next week to continuous probability distributions, sometimes that's where it's more useful to think of this continuous distribution function, CDF. And you may see questions more like this, where so sort of this is what's the probability that is between 2, 3, and 4, right? That we just wondered about, right? This mean, and then one standard deviation down, one standard deviation up, right? So how can you get that from the continuous distribution function? So remember, the CDF tells you what's the probability that it's less than something. So here, the probability that it's less than 4 is 0.992, right? And then notice that we have to subtract the probability that it's less than 1, and we get this 0.870, and then this actually gives us the right answer. Okay, so notice that if we take this from the CDF, probability that it's less than 4, we're getting too much, right? Because it includes most of what we want. So it includes a 2, 3, 4, right? But it also has some other stuff like the probability of 0 and the probability of 1. So what we do is we chop off or throw away what we don't need. Okay, and so that's a way, because the tool the continuous distribution function is this. So we can use the tool to give us too much, too much of what we need, but we can also use the tool to give us that much, right? And then we can use that to chop off the part that we don't need, and then so what remains is what we want. Okay? And so you do have to be a little bit careful that if you want this and you actually subtracted this actual 2 amount, you would take away a little bit too much, right? And so by taking away from 1 and below, that's how you leave the 2 there. Whereas if you subtract this, then you're taking out the 2, and really you're only leaving the 3 and you're only leaving the 3 and the 4. So you do have to be a little bit careful with the discrete distributions. Okay. So let's see. We already started to talk a little bit about the C coefficients, but I wanted to say a little bit more about that. So sort of kind of think of this as when we talked about the conditional probability, right? Remember, like the whole reason to talk about conditional probability was to get to independence and the idea that you can multiply probabilities, but we had to do the division first. So here, combinatorics is this larger field, and these C and R's are a subset of combinatorics. And so, so just look at these problems really quickly. So in order to satisfy graduation requirements, students must take 1 course from each of the 3 groups: humanities, lab science, and reasoning. How many unique transcripts are possible? Right? So how do you do that? Right? You have to basically think of the number of possibilities. And so we've done these a little bit, right? So what's the number of possibilities of humanities? What's the number of possibilities of lab science? And what's the number of possibilities of reasoning? Right? And so the number of possibilities for humanities is 10, right? Lab science is 2, and reasoning is 5. So we just multiply those, right? And so 2 times 5 is 10, times 10 is 100. So there's 100 different transcripts, unique different transcripts. So now if we modify this, right, so given the list, students must take 2 humanities courses and 1 each from the other 2. How many unique transcripts are possible? Well, now we're talking about, obviously humanities, and then the lab science and the reasoning. And so the lab science and the reasoning hasn't changed, right? Oh, sorry. Lab science and reasoning haven't changed. Okay. And when you think about the humanities, what has changed, right? So there's a first humanities course and then your second humanities course, right? So that's how it's, because now you must take 2 humanities courses, right? So you have to take 1 humanities course and then you have to take a second humanities course, right? So it's actually changed by introducing this new requirement, this new position of what you have to take. Okay. So for your first humanities class, how many choices are there? 10, right? All of them are possible. Now, what about your second humanities course? 9 are only possible, right? Why? Because whatever that one was, you cannot take it again, right? So before is a little bit easier, where all of them are possible. That's easy, right? So here, just like before, the first one, you have 10 choices. But now for your second one, you cannot repeat, you can't take that course twice and get credit for it, right? You have to take a different one, right? And so we know that 10 times 2 times 5 is 100 from before, times 9, that's 900. Okay, and so again, from the given list, you just take 2 humanities courses, 1 lab science, and 2 reasoning courses, right? So again, H1, H2, have to take a lab class. Now we have R1 and R2, right? So the lab class is easy, right? Reasoning, first one, and humanities, first one, those are easy, right? Might as well do the easy ones first. Then, just as before, right, this one's 9. So this is actually the same as the previous one. Now this one, right, it's got to be 4, right? And so then this 2 times, or we have basically have 900 times 4, and then we have 4 that we're multiplying it, and so now we have 3,600. Okay, or, you know, if what happens if they had said, you know, 3 humanities courses, right? In this one, then it would be, the first one would be 10, second would be 9, and the third one would be 8, right? Because the third one, you cannot take this one for credit, you cannot take that one for credit. So of the remaining ones, there's only 8 that's remaining, but you can choose any one of those 8. Okay, so you'd have that. And so basically, factorial is, you know, n all the way multiplying all the way down to 1. And so if you have, you know, 3 items and you want to arrange them in the store's window, how many possible ways? That's basically 3 factorial. Okay, 3 factorial. Okay, so now suppose you want to put them in a line. There's room for 3 items, but you have 5 items. So now there's 5 items, and you want to choose 3. So basically, there's 5 items, and then so item number 1. So first, second, and third, right? So there's 5 items to choose from, and then 4 times 3. So this is actually NPR, right? So here you can see that's 20 times 3, that's equal to 60. But if you just quickly go to your calculator, you can do 5, and then the second P, and then 3, and then that equals 60. So that's actually what it's doing. And so if you have, you know, the permutation, basically, this is the, or sorry, factorial. Factorial means use all of them. So if you have 3 and then you use all of them, you go all the way down to 1. Permutation is you have a larger number and you pick a subset, and order matters. So order matters. Right, so like the display window, you want one thing on the left, something in the middle, something on the right-hand side, so those 3, so the order matters. On the other hand, if you have a club, right, and then it's president, secretary, and treasurer, so here you use permutation because order matters. On the other hand, if you want to select a committee, right, so here you have president, secretary, and treasurer. So the order matters because the first one you pick, so number 1, say, would be president. Number 2, 2 would be secretary. Number 3, treasurer. Okay, so the order matters. Here it's a committee, and so you just want the 3 people, and the order that you select them doesn't matter. So that's when we go back to the C, the combination coefficients. And so this sort of tries to tell you a little bit more about that stuff. And then there's a classic problem, you know, how many different ways are there to arrange the letters in Mississippi? So it turns out, if you look at it, there's 11 places, right? So that would be 11 factorial, but the I is repeated 4 times, the S is repeated 4 times, you know, the P is repeated twice, and so you divide out by each of those. So anyway, that you don't have to remember that. Basically, that's all sort of trying to explain why is it that it makes sense for this C combination to have these divisions on the bottom. Okay, and so next time we'll look at you know, this quadratic expression in terms of the binomial coefficients and the cubic expression in terms of the binomial coefficients, because the order doesn't matter. Okay, so see you next time. Yes, go ahead.
Quick question about
Yes.
the number.
Okay.
Yeah, so I know how to get the.
Oh, the one that's was due today?
Yeah.
Okay.
I had to look at the solutions and figure it out like backwards. But like,
Oh yeah.
I know how to get this. Can you just
Okay.
go on Excel and you put in the stuff?
Right, good.
But I don't know how to get the second one. So that was the hard part for me. How do you get the second table?
What is the second? Oh, that's the cumulative distribution function, right? So this one, if you look at it, right, this is, do you know which function this is? Wait, why does it say CDF? Oh, go back there. CDF.
It's like the exact same, so I didn't know.
Oh. Really? Wait, let me see this problem. This is the second problem?
So you just put 0.34.
Where we go back up? This is this problem, right?
0.34.
Oh,
and you put 5.
Oh yeah, that's bizarre.
And
Okay.
you just put 0, 1, 2, 3.
Right. So if you go back down, this function, right?
Yeah.
So try to graph it.
Graph it?
Yeah. How would you graph it?
Oh, I'm so bad at
Go
graphing.
ahead. No, just go ahead. Just graph it.
Oh, wait, does it go up here? The K? Or is it in the,
Right.
It's in the bottom, yeah.
K is on the
Yeah.
X. Yeah.
Oh. Wait, the first one, yeah.
Just the first one.